In this video, we're going to talk about how to use the base capabilities of R to produce various types of graphics. And in fact, the plotting capabilities of R are one of its most powerful and attractive features. So in this short little video, we're going to talk about how to construct a histogram, how to produce box plots and parallel box plots, some scatter plots, etc. There are a number of other plots that we could talk about, but these are the plots that we're going to focus on. So a histogram is created in R using the hist function. A box plot is created using the box plot function, and a scatter plot is created using the plot function. So let's look at some examples of each type of graphic. So a histogram with a custom x-axis label and title can be created using the commands below. So what we're going to do here is we are going to draw 100 values from a normal distribution with a mean of 100 and a standard deviation of 10. We're going to assign it the name x. Then we're going to use the hist function on x, and then if we use the xlab argument, we can change the x-axis label to whatever we want. And then if we specify the main argument, then we can provide a title for the graphic. So if we ran this set of commands in R, we would get the following histogram produced by R. Okay, so it's very simple, very straightforward. We're not going to talk about all the different features that you can specify in the histogram function, but that's how you create a basic histogram in R. And if you want more information, of course, you can use !hist and look at some of the various options. We're going to talk about two different kinds of box plots in the next set of code. We're going to talk about a regular box plot and then parallel box plots, which is when you have data values separated into different groups. So let's generate some more data. So we're going to draw 100 more random values from a normal distribution, this time with a mean of 80 and a standard deviation of 3. And we're going to assign the 100 set of random values we sample the name y. And then if we use box plot, the box plot function on y, we're going to get the following graphic, at least based on the data that I drew in this particular example. So pretty straightforward. So here's our box plot, right? So we have the minimum value, we have the maximum value that are extending out from the first quartile or the 0.25 quantile and the 0.75 quantile or third quartile. And this thick line right here is the median of the data set that we had. And in this case, there doesn't appear to be any outliers, which if there were outliers, they'd be shown by little dots here outside of these whiskers. So that's how we create a single box plot in R. But what if we had data for different groups and we wanted to create a set of parallel box plots where each group had a different box plot, but we put them next to each other so we could see how they were related? So what I'm going to do here is I am going to create a factor variable, GRP or group. And what I'm going to do here is, essentially what I'm going to do is I'm going to base it off the vectors x and y up here. So there's 100 values in x and 100 values in y. And so I'm going to create a vector group 1 and group 2. I'm going to use the rep function to replicate each of those values 100 times and convert it to a factor. Then I'm going to combine the x and y vectors into a single vector called dat. And then I can use this special notation box plot of dat tilde group. And in this case, I'm going to specify an x-axis label of group. And if we executed these commands and you had the same data set as myself when I drew all the data above, then you would get the following parallel box plot shown in this graphic right here. Let's talk about scatter plots. So a scatter plot of two numeric vectors x and y can be created using two different kinds of notation. So we can use plot x comma y, where x is going to be the values on the x-axis and then y is going to be the values on the y-axis. Or we can use the alternative notation plot y tilde x, which still has x on the x-axis and y on the y-axis. So what I'm going to do here is I'm going to generate some new data. So x is 20 values drawn from a uniform distribution with a minimum value of 0 and a upper bound of 1. So we have 20 values there, and then I create this vector y, which has a linear relationship with x, and so basically I have 2 plus 3 times x, so that's a straight line. Then I add some random noise from a normal distribution into y, and then I can use the notation plot x comma y to get the following graphic, or if I use plot y tilde x, then I get the exact same graphic down here. And similar to before, we can customize the x-axis and y-axis labels using the xlab and ylab arguments respectively. So that's what I've done in this command right here. So I've changed the x-axis label to first variable and the y-axis label to second variable. And by default, there's actually no title produced. And so I can actually add a title using the title function after the fact. And so I've called the title of my plot, title of plot. And so we have an example of another scatter plot here with some slight customizations to the x-axis, the y-axis, and to the title of the graphic. There are some other arguments for the scatter plot function that I want to provide. So one of those is that you can create a scatter plot where we connect the points with lines instead of having dots. And so we can do that using type equals L, though usually this works best for things like densities and stuff like that. You can also specify type equals B, which will display both points and the line. So I'm going to show a couple of examples with those. So I'm going to create a sequence of values between -4 and +4 of length 1000. And then I'm going to evaluate those values of x. We're going to evaluate those based on the density of a normal distribution with a mean of 0 and a standard deviation of 1. So this is the bell curve you've probably seen in a statistics class or a data science class. So I'm going to store those density values in a vector y, and I'm going to use plot x comma y. I'm going to have the x-axis label be equal to x, the y-axis label be equal to density, and I specify type equals L. And you notice that now I have this nice smooth set of values that are connected to one another as opposed to the points like I had above. And then I've titled it density of standard normal. So in order to display the type equals B, where I have both the lines and the points in one graphic, I've done the same plot, but instead of having 1,000 values, I've only shown 25. Otherwise, the dots start to overwhelm the plot. But otherwise, things are pretty much the same. I've just changed the name of my variables to x2 and y2. I plot that using the alternative notation here, using type equals B. And you can see that in this graphic, I have the points, and then I connect a line between the different points. So that's pretty nice there. One other option you should be aware of is that sometimes you want to use type equals H, which essentially is used for a histogram-like plot. And this is particularly useful when you're trying to plot the probability mass function of a discrete random variable. So consider an example where we had a binomial distribution with 20 trials and a probability of a success equal to 0.3. So in that case, it means that the values of x can take any values between 0 and 20, because if I had 20 trials, I can have 0 successes all the way up to 20 successes. And then I'm going to evaluate each one of those outcomes using the probability mass function of a binomial distribution for size equal to 20 and probability of success equal to 0.3. I'm going to store those probability mass values in a vector called y. Then I do plot x comma y. I specify the x-axis label and the y-axis label, and I do type equals h, which creates these vertical bars that go from the probability mass value all the way down to 0. And then I've provided a custom title here. So that's how I created a probability mass plot for the binomial distribution. So now we have another your turn. So I'd recommend pausing this and seeing if you can't do these yourself. I'm going to read through these real quick, and then I will show you the code that I've created to do this already. So you may want to look at some of the distributions available in R, so use question mark distributions to do that. And then once you do that, you might want to draw 1,000 observations, or I'd like you to draw 1,000 observations from a Poisson distribution with a mean of 10 and assign it the name V. Then use the table function, which we have not talked about, but that function will tabulate a contingency table based on the values of V and store the tabulated values in an object called tab V. So tab V is a contingency table. The top row, as we'll see, is the observed values in V, and the bottom row is going to be the number of observations with each value in that top row. Use the SCR function to look at the structure of tab V, and then you can actually use the plot function on tab V. And we'll see you'll get something interesting when you do that. And the reason for that is that plot is actually a generic function, which means that depending on the type of object you give it, it sometimes knows that it can create a certain kind of plot. And so there is a plot option for a table an object of class table. And so because that plot method is available, it automatically generates an interesting plot that we'll see shortly. After that, use the names function to extract the names of the observed values in V. We'll assign this name value underscore char or char because this is, as you'll see, these are character values. And we'll see that using the str function. And then so we're going to convert those character values into numeric values using the as.numeric function and assign that the name value. Lastly here, before we start doing some plots, we are going to convert tab v to a vector, a numeric vector, using the as.vector function. We'll assign it the name counts, which we can verify using the str function. So after that, we will construct a histogram of the counts, we'll construct a box plot of the counts, and then construct a histogram-like plot of counts using the values variable on the x-axis, or actually I guess it should be value technically, based on what I've done up here, and the counts variable on the y-axis. So now we'll go over to RStudio and actually look at that. So if I do question mark distributions here, we'll see that we get a lot of information about the different distributions in R. We might want to look at the Poisson distribution, and that has a parameter lambda. And if we look closely at this, we will find out that the mean of our random variable is lambda. So lambda specifies the mean of the distribution. So if I want to draw 1,000 observations from a Poisson distribution with a mean of 10, I can use this command, and then I will assign it the name v. I want to then tabulate the observed values of v. So I'll look at them there. So we have 1,000 values. They're all integers because Poisson random variables have to take integer values. So we tabulate them using the table function. Okay, so now we can look at tab v. And this is a little hard to read, but this top row, which kind of wraps around here, shows which count values were observed in V. So we have 2, 3, 4, 5, 6, 7, all the way up to 21. So we didn't observe any zeros or ones or 22s, but we did observe at least one value for each of these other numbers. And then the bottom row, or the lower row here, shows how many times each of those values was observed. So there were 2 2s observed, there were 4 3s observed, 23 4s observed, etc. So if we look at the structure of this, it's a little weird, but we can see that it's of class table. We see an integer vector of 20 values, so we saw 20 different unique values in V. And there's some other attributes and things like that which we have not talked about. And this takes time to learn how to do this in general. This is just a crash course, but we will learn how to do some manipulation here for our tab V object. So let's use plot. So if we do that, we actually see a histogram-like plot, similar to what we saw in previous graphics. And then I want to use the names function on tab V here, so that we have each of the different values that were observed in V. So I'm going to extract that and store it in value underscore char or char. And as we see here, this is a character vector of length 20. So this is not going to be useful for creating a plot, because these are character values and not numbers. So I want to use the as.numeric function to convert these character values into regular values. Okay, so if we look at value now, we can see that's just numeric value, so that's good. And then I want to convert the tab v object to just a regular vector using the as.vector function. I store that in counts. Okay, so I have 2, 4, 23, all the way up through the last element, which is 2 values of 21. If I look at the structure of counts, I see it's an integer vector, which makes sense since the Poisson distribution only has integers. And then now that I've converted everything, I can construct a histogram using the hist function. I can construct a box plot using the box plot function. Or if I wanted to construct that histogram-like scatter plot, I can use the counts function the counts variable as the y variable and the value function as the x variable. Specify type equals h. And I get my histogram-like box plot, or my histogram-like scatter plot.